So we're going to pick up with our discussion of climate proxies with discussing what stable oxygen isotopes tell us. So oxygen isotopes are really useful for making inferences about global temperatures. There are 3 oxygen isotopes that are all stable. Oxygen-16, which consists of 8 protons and 8 neutrons, is the most abundant. Oxygen-17 is only really available in trace amounts, but it consists of 8 protons plus 9 neutrons. And then oxygen-18 is actually fairly abundant as far as isotopic concentrations go, and it consists of 8 protons plus 10 neutrons. So these are the naturally occurring concentrations, but as you might expect, if we're going to use them to make inferences about past climate, there's got to be something that induces fractionation. And it turns out that that something is evaporation. We'll get there in a moment, but first of all, let me tell you where the oxygen in the rock record that we're measuring is coming from. So the oxygen isotope ratios within calcium carbonate of living organisms, benthic foraminifera. So benthic basically means bottom dwelling in the ocean. And the foraminifera are the type of organisms that they're actually a type of amoebid protists, and they're characterized by a streaming, hold on, let me finish writing this. Getting distracted. They're characterized by a streaming granular ectoplasm that, among other things, is used for catching food, and often they have an external shell made of various materials, but those materials always have calcium carbonate in them, and so they fossilize pretty well, and the calcium carbonate does a pretty good job of telling us about the marine environment in which this is what they look like in fossilized form. Pretty cool looking. But let's get into the mechanism. So I told you already that evaporation induces fractionation. And this is also somewhat intuitive. Evaporation tends to favor light isotopes. Light isotopes have a little bit lower mass than heavy isotopes, and so they're better able to escape the water surface into vapor form. Likewise, in clouds, heavy isotopes, which are a little heavier than the light isotopes, are ones that preferentially rain out first. And so as water vapor persists in the atmosphere, it becomes more and more light. And ultimately, the precipitation that falls in polar regions, a lot of that water originates from evaporation in warmer regions. And so the precipitation that forms the ice sheets is isotopically light. So when you have ice sheets covering the globe during, say, colder periods of time, that means that the remaining oxygen isotopes present in the oceans and present in the atmosphere are relatively heavy, just because so many of the light isotopes are trapped in the ice. Okay, so during cold periods, light oxygen is trapped in ice sheets, leaving the remaining oxygen in water heavy. And it's those heavy isotopes that are not trapped in the ice sheets that are preserved in the ice record. So, or in the rock record, I should say. So heavy isotopes in rock record means cold conditions. Here's another view of this mechanism. A lot of water evaporates over warmer parts of the Earth. We'll learn in atmospheric circulation how that moves, but as those air masses move towards the poles, more and more of the heavy isotopes rain out, and as you go in this direction along the arrow, the water vapor becomes increasingly depleted in oxygen 18. It becomes lighter and lighter. And so the snow in the interior of Antarctica and in the Arctic has a lot less oxygen 18 than ocean water. And so during periods of time climatically, when ice sheets cover more of the planet, what that means is that ocean water is more rich in oxygen 18 and is heavier. And it is that heavy signature that is then preserved in the foraminiferous shells and recorded in the rock record. So the way that we measure how heavy or how light isotopes actually are is through a process that involves the isotopic ratio. So the isotopic ratio is the ratio of the rare isotope, which in this case would be oxygen 18, to the abundant isotope. It's always formulated so that it's less than 1. But the problem with these ratios are that they're not terribly intuitive. For one, the rare isotope abundance is usually so much less than the abundant isotope that you end up with these really, really small numbers that are hard to compare to each other. And so it's actually more useful to compare the isotope ratio of a sample to some standard. In other words, is my sample of oxygen isotope ratios within this foraminifera case heavier or lighter than ocean is today? And so the way that we compute this is with a relative abundance. That's called the del value. So del oxygen 18 is equal to the isotopic ratio of the sample minus the isotopic ratio of some standard, normalized by the isotopic ratio of the standard. And again, this is a really small number, so we multiply it by 1,000 to make it something that's a little bit more reasonable to deal with. And these isotopic ratios, because they're multiplied by 1,000 and not 100, are given by what's called per mil rather than percent. So you're familiar with percent, which you get by multiplying a fraction by 100. When we multiply it by 1,000, it's called per mil. Now, the standard that is used for oxygen isotopes is known as Vienna Standard Mean Ocean Water. It's basically the isotopic composition of ocean water today. And it is quantified in a really rigorous and reproducible way. So just as a way of reviewing, let's compute this coupling diagram. So with warmer temperatures, well, let's actually start with colder temperatures. So we could think of more extensive ice sheets over the Earth. So with cold temperatures, we have a higher amount of O16 locked in ice. So what that means is that the ice sheets are larger with low temperatures. Okay, so low temperatures means higher amount of oxygen 18 locked in ice, and so we could draw a negative directional coupling from temperature to the amount of O16 locked in ice. So what that means is that oxygen 18 is going to be, in ocean water, is going to be high when a lot of O16 is locked in ice. So high O16 locked in ice means high O18 of ocean water. So we have a positive coupling from that middle box to the box on the right here. Okay, so high temperature. So if we look for a direct connection between temperature and O18, what this means is that high temperature means low del O18, whereas low temperature means high del O18. And the way we get this is just by multiplying this -1 we have here by this positive one to recognize that there's a negative coupling from temperature to delta O18. Okay, so I could just go ahead and draw that in maybe a different color here. So if we're just interested in this coupling, it's a negative coupling. And that's how I get this statement down here. So we can look at the dull oxygen 18 record to make inferences about previous temperatures. So it's conventional on these plots to see these dull O18 numbers increasing as you go down. And that's because we tend to think about high temperatures high on the axis, low temperatures low on the axis, and there's this negative relationship from oxygen O18 to temperature. And so that's why this is usually shown on a reversed axis. So hotter temperatures are up here. The present day period of time, or the end of the Pleistocene, is over here, so we're going back in time as we go in this direction. So one of the things that we could see is that over the past 70 million years, the Earth was a much warmer place, and we've gone through this progressive cooling throughout the Cenozoic. But then if we zoom in on the Pleistocene specifically, what we see is a lot of fluctuation. So again, on this plot, del O18 is low down here, or is high down here, low up here. This means high temperatures here, low temperatures here. So if this is the present day and age, you would guess that we're in an interglacial phase, meaning that this is not, oops, I meant to do that. So we're in an interglacial phase. We're not under these glaciated conditions that we were at the end of the last ice age, which is right here. So I think I will go on and go into what these oxygen isotopes tell us about the Pleistocene glaciations. Well, as we just said, the Pleistocene epoch evolved from a gradual cooling of the Earth throughout the Cenozoic era. So right now, in this diagram, the present day is right here, and we're going back in time as we go to the right side of this graph. And here's that gradual cooling that we saw in the graph that we looked at previously. Then, as we get into the Pleistocene, we see a lot more fluctuation in temperature, quite a bit of fluctuation, in fact. So the start of the Northern Hemisphere glaciations, that's this NH abbreviation, as told by the record of benthic foraminifera in the North Atlantic, was about 2.8 or so million years ago. And this was during the Pliocene. These glaciations continued into the Pleistocene, and then the last glacial, or the last ice age, was right here on the plot. Okay. Now, there's a few interesting things that you'll notice from this. One is that the frequency of the glacials seems to change around 700,000 years ago. They're very frequent in Earth's long-term history when they occurred at around these 40,000 year periods. But in recent history, they became a little bit higher in magnitude, so larger swings, and they became less frequent. They started occurring at 100,000 year intervals instead of 400,000 year intervals. So that's interesting, and it's still a little bit of a mystery as to why that shift occurred. In the next lecture, we'll get into the mechanisms that caused the shift. But first of all, I just want to go through a little bit of terminology. So we call interglacial periods of time the warmer periods of time when oxygen 18 is a little bit lighter, and the glacial periods of time are the colder periods of time. Okay, so we're currently in an interglacial phase. The last time the northern hemisphere was covered in ice was around 18,000 years ago. So the last glacial interval started 18,000 years ago, but lasted until about 9,500 years ago. And during that period of time, the global average surface temperature was about 5 to 6 degrees Celsius lower than it is today. During that period of time, a continental glacier covered North America with ice that was about a mile thick over Canada. So next time you have to walk a mile, just imagine that that's the thickness of ice on top of you. And we don't want to go back there. But I think one thing that's really interesting to emphasize is that when we're thinking about climate change in the future, a lot of times we're talking about a climate change of just a few degrees up to maybe 4 degrees over the next 100 years or so. But a 5-degree difference led to such a huge difference in terms of the global ice coverage, and particularly the ice coverage in North America. So it might not sound like a lot, but 4 to 5 degrees Celsius is actually quite significant in terms of what this means for life on our continent. So anyway, that just puts this in a little bit of perspective. I believe that's not all I have for you yet today. I just wanted to point out that in Earth history, there were 5 main glaciation periods. So there were 2 in the Proterozoic. You're familiar with these. These are the snowball Earth events. Then there was another one that coincided with the rise of oxygen. And there was a short one in the late Ordovician. There was another long series of glaciations that actually coincided with high oxygen. And then in the past 2.5 million years have been the Pleistocene glaciations. Now we're still in a glaciation period. We're still in this general period of time where temperatures are fluctuating between interglacial and glacial phases. We're in an interglacial phase within a glaciation period. Okay, so these are called the Pleistocene glaciations, but they actually, as you saw, started in the mid-Pleistocene. And I think I will skip over this and just get to the summary here, which is that over the last 2.5 million years, there have been many glacial intervals or long-term periods, short-term periods of time that we call ice ages. And those alternate with interglacial intervals, which is what we're in right now. So we have several pieces of evidence for the existence of these large continental ice sheets during the glacial intervals. One is we've got geologic evidence, things like rocks that are far from the locations in which they originated. These are known as erratics. We have U-shaped valleys that could have only formed when large glaciers were moving through them. We have moraines, which are sediment deposited at the tail end of the glaciers. So there's a number of different geological features that we associate with glaciations. We have evidence from biology, evidence of records of vegetation change as temperatures changed in these areas. And then we have the most important thing that we've emphasized really here is oxygen isotopes within sediment and within benthic foraminifera. So key features discovered in these climate proxies are that these glacial interglacial cycles throughout the Pleistocene have both 41,000 year intervals and 100,000 year intervals. It's the latter that are the most recent, okay? And as we'll learn in the next lecture, these are linked to Earth's orbital variations. This is really the driving mechanism for shifting into and out of these glacial intervals. And as you might expect, they're also correlated with greenhouse gas concentrations, which go up during the interglacials and down during the glacials. But I'll leave that for lecture on Tuesday. I hope you guys have a good weekend, and I'll see you soon.